All right, welcome back to another lecture. In this lecture, we'll cover section 1.4 about boxplots. Before we dig in, make sure to go to lecture 1.4 on Canvas, download the notes, and download the data set for this data. So let's dig in. We have talked previously about histograms, which are one graph for displaying numerical data. Boxplots are another way to display numerical data, and this is what a boxplot looks like. Okay, so a boxplot is going to show the minimum value in the data set. It's going to show the minimum value in a data set, the maximum value, any outliers in the data set, as well as quartiles. Now we haven't talked about quartiles yet, and so that's the first order of business, right? We're going to begin by talking about what quartiles are, what outliers are, and then we can come back to boxplots and talk about what boxplots do for us visually. So the quartiles of a dataset are the markers that split the dataset into 4 chunks with an equal number of observations in each chunk. Okay, so in other words, about 25% of the data in our dataset are going to be below Q1. That's the first quartile. And about 25% of the values in the dataset are going to be between Q1 and Q2. That's the second quartile, or another word for the quartile is the second quartile is the median. We'll talk about the median in more detail in a later section. And so forth, right? So 25% is between Q2 and Q3, and then 25% is above Q3. Note that there is no fourth quartile. There's no such thing as Q4, and that's because if you're going to take a data set and split it into 4 parts, you only need 3 divisions to do that, right? Because if you divide the data set once, then you have 2 halves, right? And then if you divide each half in half again, then you'll have 4 quarters. So it only takes 3 quartiles to split the data into 4 parts. To find the quartiles by hand, we'll do exactly what I just said, right? First of all, we'll put the values in order from smallest to largest. And then we'll find the middle value, right? The middle value of the entire data set is the second quartile, or in other words, the median. Then we'll look at the lower half of the data and we'll find the middle value in the lower half, and that's the first quartile. And then we'll look at the upper half of the data set, and the middle value of the upper half is the third quartile. That's how we would do it by hand. We can also find quartiles from Art of Stat, okay? But I want to practice it both ways, at least at first, just so that you get some understanding of what quartiles are. So that's what example 2 asks us to do. It says find the quartiles of the following dataset by hand and in Art of Stat. These values are not quite in order, so the first order of business is going to be to rearrange them. I think that the smallest value I see is 30, so that should come first. I'm going to scratch these off as I go. So 30, and then it looks like 48, 49, 50, 51, 52, 53, 54, and 55. Okay, so here's our list now in order from smallest to largest. To find the quartiles, the first thing we do is find the second quartile, right? That's the median, or in other words, the middle value in the data set. In this case, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 values. So the middle value should be in position 5. I think that's this one here, right? This way I have 4 values below it, right? 4 values below it, 4 values above it. So that's my median. That's my second quartile, okay? So this is Q2. Next, I'm going to find the median of the lower half, right? So I'm going to look at just these 4 values and try to find the middle value there. And here we run into a little bit of a difficulty because there are only 4 values. And so there's no value that's right in the middle, right? If I choose 48, there's only 1 value below it, but 2 values above. And with 49, I have just the opposite problem. So what we do in this case is we take the number that's right in between the 2 numbers in the middle. So in the case of 48 and 49, the value that would be right in the middle would be 48.5, right? 48.5. So that's going to be Q1. Similarly, on the upper half, right, I've got these 4 values. Since there is an even number of values, there is no value that's right in the middle. So I'm just going to take the one that comes right in between 53 and 54, and that's going to be Q3, right? So 53.5 is Q3. Okay, let's head over to Art of Stat and see if we can do the same thing in Art of Stat. So first of all, I've got the data here. I'm going to go ahead and select these values and copy them. And then I can head over to Art of Stat. And I'm going to go to Web Apps. And I'm going to open up the Explore Quantitative Data app. And I want to do my own. And then I'll just paste values there. So you'll notice that in addition to giving us a histogram, it also gives us a box plot, okay, which we'll talk about in a second. For now, I'm just going to hide those things because the main thing I want to see is this list of descriptive statistics. And in particular, Q1 is here, Q2, which is the same thing as the median, is here, and Q3 is here. And you'll notice that that matches up precisely with what we got when we did this by hand. As a caveat, I would just say that this doesn't always work out. Sometimes technology will compute things differently than we do when we go to compute stuff by hand, and that's okay. The values are usually pretty close, if they're not exactly the same. And I think we shouldn't have that problem in Art of Stat, because I think that Art of Stat will compute these quartiles the way that that we just went over when we did the calculation by hand. But just know that, you know, if you're using Excel or some other tool, you might get slightly different values, and that's okay. So with quartiles in hand, we can talk about outliers. So first of all, the difference between Q3 and Q1 is called the interquartile range. That's the distance between those values, right? So in other words, the IQR is Q3 minus Q1. The IQR is an important statistic in its own right, and so we'll talk about it in a little more detail in a future section in this course. But for now, we're just going to use the IQR to compute fences, because those fences allow us to identify outliers, okay? So an outlier is an unusual observation. For numerical data, an outlier is any value that is substantially smaller or substantially larger than the majority of values in the data set. There are going to be different criteria for determining what we consider to be an outlier, but a pretty widely accepted one is the one that I've given here, and this is how we'll identify outliers in this class, right? What we'll do is we'll say, well, we're going to compute these two things called fences. Okay, we've got the lower fence here and the upper fence here. And any value that is below the lower fence is going to be considered an outlier. And any value that is above the upper fence is also going to be considered an outlier. In other words, so we'll compute these fences. Anything inside the fences is good. It's normal data, right? Anything outside the fences is going to be considered an outlier. That definition is somewhat arbitrary, but here's a picture, right? Here's a picture to kind of show you why it seems like, that's a fairly decent way of determining what an outlier is. So we've got Q1, we're pretending that Q1 is here and Q3 is here. So that means that half of the data is between Q3 and is between those two marks, right? Half of the data lives there, 50% of it. Well, if half of the data is within these two marks, our lower fence would be that distance times itself, well, 1.5 times this distance, basically. And then you subtract that from Q1, and that would land you all the way kind of down here at the lower fence. Similarly, the upper fence is going to be the distance between Q1 and Q3 times 1.5, right? And then we add that to Q3, and that would put us all the way up here. And so we're saying like, okay, if 50% of your data lives here, then any data that's between the lower fence and the upper fence is going to be like pretty normal data. But if you're outside of those areas, like those are some pretty unusual values, right? And anyway, so that's the idea behind fences and outliers. I should say before we go any further that a data set might not have any outliers, right? Or it could have one outlier, or it could have multiple outliers. So anything goes. To calculate fences and hence find the outliers, we'll follow this procedure. First of all, we'll use ArtofStat to calculate quartiles and IQR, and then we'll have to just use a calculator to calculate the lower and upper fences. And then any value in our data set that's below the lower fence or above the upper fence is an outlier. So let's practice doing that. So number 2 here says, the data below represent the monthly salaries of 16 employees at College of the Sequoias. Calculate the fences and use them to determine if the data set contains any outliers. Okay, well, you're welcome to pause the video and give that a try. I'm going to go ahead and walk you through my solution. So first of all, I'm going to head over to ArtofStat. Actually, I need to grab the data real quick. So let me select the data, copy, and then I can paste that into ArtofStat here. Okay, so now I get Q1, Q2, Q3. I also have the IQR. So in my notes, I'm just gonna say that like I used a ArtofStat. I'm gonna abbreviate AOS, and I would ask you to do this, please, on problem sets and tests and things to kind of show your work, to show me where you're getting your answers. Just say like, oh yeah, I went to ArtofStat, and so maybe I'll say from ArtofStat, I'm getting the following values for quartiles, right? Q1 is 5,300. I don't really need Q2. I don't really need the median for this calculation. So I'll just write down Q3, which is 5,800. And then the IQR is just the difference between Q3 and Q1. You could do that in your head, right? 5,800 minus 5,300 is 500. But also ArtofStat happens to do that calculation for us, right? And it already told us that the IQR was 500. Okay, so then as far as the fences are concerned, now we're going to have to do those calculations ourselves. So lower fence is Q1 minus 1.5 times IQR. And again, I would like for you to show your work this way. Show your work the way that I'm laying it out. If you don't, you'll be marked down. So lower fence is Q1 minus 1.5 times IQR. Q1 is 5,300. And IQR is 500. So let's head over to our calculator and see what that is. Actually, maybe before we do that, let's write down the upper fence, right? So the upper fence is Q3 plus 1.5 times IQR. So notice the subtle differences between the lower fence and the upper fence. We have Q3 for the upper fence rather than Q1, and it's a plus rather than a minus, okay? But this is going to be 5,800 plus 1.5 times 500. Okay, so let's head over to a calculator. I'm going to use the Desmos calculator as usual. So desmos.com. And then I'll open up the scientific calculator. And then I can just punch in these values. Let me show you something that students will sometimes do wrong here. Sometimes they'll want to do this one step at a time. Like they'll say 5,300 minus 1.5 and then hit enter. And then they'll take that value, negative 5,298.5 and multiply it by 500. And that's incorrect. The reason that's incorrect is because you're not following the correct order of operations, right? Order of operations says that we have to do multiplication first. So really we should do 1.5 times 500 first, and then take that value and subtract it from 5,300. The good news is that Desmos will do this for you. If you just type the value in exactly the way it looks on your page, Desmos will do this correctly. So if you just type in 5,300 minus 1.5 times 500, now that's the correct answer, right? It should be 4550. This is one of the reasons why I would encourage you to use a real calculator rather than the calculator on your phone, because a lot of times the calculator on your phone is just kind of like a basic calculator that will do the operations in the order in which you type them in, which doesn't always match the correct order of operations. So if you're using your phone and you ended up with this value, it's because your phone is not using the correct order of operations, right? This is the value you should come up with. And if you just use the Desmos calculator and type it in exactly the way that I've shown you here, you can't go wrong. Okay, so there's the lower fence. And let's look at the upper fence. So that should be 5,800 plus 1.5 times IQR. Okay, so that's 6,550. Let's head back over to the notes, write those down. So we've got 4,500 for our lower fence, and, or sorry, not 4,500, 4,550, right? So 4,550 for the lower fence, and 6,550 for our upper fence. Okay, we still haven't identified any outliers, right? These are just the fences. Notice that these fences, they actually aren't even in the data set at all, right? So the fences aren't in the data set. They're just markers that we use to determine if we have outliers, right? So on the lower end, we can look to see if we have any values below the lower fence. And on the upper end, we can look to see if we have any values above the upper fence. So on the lower end, we're looking for values below 4,550. And it looks like we've got one of those right here, right? 2,200. So that's an outlier. On the upper end, we're looking for values bigger than 6,550. It looks like we've got two of those, right? We've got 6,800 and 7,200, both outliers. Okay, so our outliers, if I can squeeze this in, outliers are 2,200, 6,800, and 7,200. Okay. Part B asks an interesting question. I'm not sure I'm going to write anything down, but it's worth discussing. It says, any ideas as to what might be the cause of the outliers? Well, I'll let you kind of pause the video and think about that. Remember that these are supposed to be the salaries of COS employees. So, particularly on the lower end, right, 2,200 seems a lot lower than everybody else's salary. Why might that be the case? I would suggest that maybe this employee is part-time and everyone else is full-time, right? That might be a reason for it. On the upper end, even though these values are outliers, they're not quite as drastically different, from the rest of the data as 2,200 is, right? So I don't know. These people are just, I guess, senior, employees who have been there for a while and kind of gone up, in the pay scale, or maybe they're managers or something like that. Whatever. None of these salaries are up to date, I think. I think most COS employees are probably making a little bit more than this at this point. But anyway, that's neither here nor there. Moving on. So now that we know what quartiles and outliers are, we can talk about boxplots again. So a boxplot is a graph that displays the quartiles, outliers, and minimum and maximum values that are not outliers. And so this is kind of the breakdown. We call these things whiskers. So that's the lower whisker and the upper whisker. And then the thing in the middle we call the box, right? So the whiskers go down to the minimum and maximum values that are not outliers. And then if we do have outliers, then those will be marked with just like a little dot or an asterisk or something like that. As far as the box is concerned, the left portion of the box, the left boundary of the box is the first quartile, and the right boundary of the box is the third quartile. The line that's somewhere between those values is the second quartile, or in other words, the median. Okay, and I didn't draw it here, but a box plot always has to be fitted to some kind of number line so that we know, what these values are. So maybe this is like 5, 10, 15. I'm doing a terrible job. These should be spaced out evenly. 5, 10, 15. 15, 20, right? 25, 30, whatever. And so then you can see that, okay, so the median is like, it's about 12, something like that. The third quartile is maybe 16, 17, right? The outlier is, 29 or something. Anyway, so box plots should always be fitted to a number line like this. Let's look at some examples here just so that we know how to read a box plot, so we're sure that we're comfortable with what it's communicating to us. This one says the side-by-side box plots compare the pulse rates in beats per minute of 19 students before and after gentle exercise. They just had to rub it in our face and say that it was gentle exercise, right? Okay. So part A says, before exercise, about what percentage of students had pulse rates between 70 and 90 beats per minute? So the box representing the students' pulse rates before exercise is the one on the bottom, right? And we're looking for what percentage of students in that bottom box plot had a pulse rate between 70 and 90 beats per minute. That's about here and about here. Well, we know that this is the first quartile and that this is the third quartile. And we also know that this middle line is the second quartile. And the quartiles split our data set into 4 equal parts. So 25% of the data lives out here above Q3, and 25% of the data lives down here below Q1. And 25% of it is here, and 25% of it is here. Okay, so if we're looking for what percentage of students had a pulse rate between 70 and 90, that's between Q1 and Q3, well, it would be 25% plus 25%, right? 50%. 50% of them. Okay. I'll let you pause the video and give the rest of this a try. Here are my solutions. For part B, it says before exercise, so still looking at that bottom box plot, about what percentage of students had pulse rates less than 90 beats per minute. Less than 90, so less than this marker right here, that would be 25 plus 25 plus 25, 75%, right? 75% of the values are below Q3. Part C, after exercise, about what percentage of students had a pulse rate less than 90 beats per minute. So now we're looking at the upper box plot, and we're looking at that same value of 90 beats per minute, and we're being asked what percentage of students had a pulse rate below that value. Well, this is Q1, Q2, Q3, and so that means 25% of the values fall below that line, right? 25% of them are here, 25% of them are here, and then 25% of them out here, right? So, so after exercise, about 25% of students had a pulse rate below 90 beats per minute. That's interesting, right? Before the exercise, 75%. So the majority of students had a pulse rate below 90 beats per minute. But after the exercise, only about a quarter of the students had a pulse rate less than 90 beats per minute. Okay, part D, before exercise. So back down to that bottom Boxplot. About 50% of students had pulse rates above what value? Well, we already know that 50% of students have a pulse rate between 70 and 90, but now we're being asked, but 50% of students have a pulse rate above what value? Well, it can't be above 70 because 75% of students have a pulse rate above 70. It must be whatever this Q2 is, right? I would call that maybe, I don't know, 76, 77. So maybe 77 beats per minute, right? About half of students have a pulse rate above 77 beats per minute. Okay, part E, estimate Q3 after exercise. So back up to that top box plot after exercise. This is Q3 right here. Yeah, I would say, 105 beats per minute. Part F, by how much did the median pulse rate rise after exercise? The median pulse rate. Well, we just said the median before exercise was about 77. The median after exercise is, well, that looks to be about 100, maybe a little less, like 99 or something. So by how much did the median pulse rate rise? Well, it would be 99 minus 77, roughly, So that's 22 beats per minute, right? Okay, so the exercise on average raised the students' pulse rates by about 22 beats per minute. Okay, part G. After exercise, what was the maximum pulse rate that wasn't an outlier? And what was the pulse rate of the outlier? Okay, so after exercise, the maximum that is not an outlier is this upper whisker. It's where the upper whisker ends, right? So that's the maximum value that's not an outlier. And it looks like that's about, 128, something like that. Okay, so about 128 beats per minute. So the maximum that's not an outlier is about 128 beats per minute. And then the value of the outlier itself, that's this dot, right? So this student really struggled. This would have been me if I were subjected to the exercise. Okay, so 145 beats per minute, right? So the outlier is 145 beats per minute. Okay, and then finally part H, before exercise, if a student had a pulse rate of 85, what quartiles were they between? So before exercise, if they had a pulse rate of 85 beats per minute, right, that's right about there, 85. So that would have put them here in this box between Q2 and Q3, right? They would have been between Q2 and Q3. All right. So hopefully that gives you a good understanding of how Boxplots work and the information that they convey to us. As you have definitely noticed, right, Artistat makes Boxplots for us, so we don't have to worry about trying to draw them by hand. Although for the purposes of like a problem set or a test or something, you might have to draw Boxplots in some blank spaces or whatever, but you can just make the Boxplot in Artistat and then copy down what you see on the screen onto your test. One warning that I would make is that the Boxplots that Artistat makes, they correctly identify outliers as far as I'm aware, but they don't correctly identify fences. So if you make a Boxplot in Artistat, and I'll show you this in a second, but if you make a Boxplot in Artistat and you hover your cursor over the Boxplot, then it'll label different things for you. It'll label the quartiles and things like that. But it'll also label the whiskers as fences, and that's not always exactly true, right? What Artistat is labeling as fences are really the maximum and minimum values in the data set that are not outliers. which isn't the same thing as fences. The fences actually don't show up at all in the picture. So if you need to know what the fences are, you'll have to calculate them by hand like we did on page 2 of the notes. Let's look at a couple examples of that. So number 4 here says, below are the recorded speeds in miles per hour of 14 randomly selected vehicles on Walnut Avenue between Ben Maddox Way and Santa Fe Street. Use Art of Stat to create a box plot of the data and then draw it below. Does the box plot indicate any outliers? Calculate the fences to verify the result from Art of Stat. Very well. Okay, let's do it. So let me grab the data. And paste it into Art of Stat to refresh the page. Okay, and I don't really need the histogram at this moment, but it's nice to have the box plot here. So there we go, right? There's our box plot. No outliers, right? It doesn't show any outliers. If I hover my cursor over the box plot, then right now it's just showing the minimum and maximum values as those lower and upper fences, and that's true, right? Those whiskers go down to the minimum and maximum values in this case because there are no outliers in the data set. But as far as I know, it doesn't show the fences. So if you need to know what the fences are, you're going to have to do that calculation by hand. So anyway, let's copy this down and then we'll calculate some fences. So to draw your box plot, first of all, remember that you have to have a number line, okay, that you attach your box plot to. And as long as you're able to draw a straight line at least as good as mine, which shouldn't be too tall in order, as long as you're able to do that, you should be fine. Then I'm going to mark 20, 25, 30, 35, and 40. And it's good to label your graphs, right? These numbers down here, they represent speeds, right, in miles per hour. So I'm going to label that speed in miles per hour. Okay, and then I can just go ahead and draw my box plot. I know from Art of Stat that Q1, I'm going to draw my box first, right? So Q1 is at 28, so that's right about there. The median, Q2, is at 32.5, right about there. And then Q3 is at 38, right about there. So there's the box portion of my box plot. And then I just need to draw the whiskers. The right whisker will go from Q3 out to the maximum, which is 40. So there's my right whisker. And the left whisker will go all the way down to the minimum, which in this case is 20. It'll go from the minimum to Q1 right there. And that's it, right? All that's missing is a title. You could call this Speeds on Walnut and Santa Fe. Just abbreviate. Okay. Clearly there are no outliers here. But we're being asked to verify that. It says calculate the fences to verify the result from Art of Stat. So let's do that. Our lower fence is Q1 minus 1.5 times IQR. Q1 is 28 and IQR is 10. 1.5 times 10 is 15, and 28 minus 15 is 13, I believe. You're welcome to do that on a calculator. You don't have to do it in your head, but in this case, I thought it would be quicker. Upper fence, Q3 plus 1.5 times IQR. Again, from Art of Stat, we see that Q3 is 38, and the IQR is 10. Again, 1.5 times 10 is 15, and 38 plus 15, oh, that's harder, but I think that's 53. 53. Okay. This verifies the results that there are no outliers, because you'll notice that our data set here is already arranged in order from largest to smallest, and there are clearly no values in the data set below 13, and there are no values in the data set above 53. So yeah, no outliers, right? It's verified. You'll also notice that these fences, 13 and 53, they don't actually show up on the graph, right? We don't indicate the fences on our box plot at all. With that in mind, let's look at another one. It says the Highway Loss Data Institute routinely collects data on collision coverage claims. Collision coverage insures against physical damage to an insured individual's vehicle. The data below, in dollars, represent a random sample of 18 collision coverage claims. Use Art of Stat to create a box plot of the data and draw it below. Any outliers, calculate fences. Same thing as example 4. So I will let you pause the video and give this one a try. Okay, so here is my box plot. And a couple things worth pointing out. First of all, we've got a bunch of outliers, right? 2 below the lower fence, 2 above the upper fence. But also what I wanted to point out is here where when you hover your cursor on the box plot, you see how it labels that left whisker as the lower fence and that right whisker as the upper fence. I just want to reiterate that that's probably not correct. What it is labeling as the lower fence is actually just the minimum value that is not an outlier. But the fence itself doesn't show up in the box plot, right? Same thing with the upper fence. What it's labeling as the upper fence is really just the largest value in the data set that's not an outlier. The upper fence itself doesn't show up on the graph. And this is why I've asked you to compute the fences so that you can see that, right? So hopefully you've done that. Anyway, let's take a look at the notes and calculate some fences. Okay, so here I've just copied down the box plot that we had from Art of Stat. And what we would like to do now is, yes, we do have outliers, right? Does the box plot contain outliers in the data set? Yes, there are 4, right? One of the things that I want to show you real quick, if you want to know what the values of those outliers are, is you can, in Art of Stat, you can sort the values from smallest to largest. And that way you can see, oh, okay, yeah, the smallest value is 530, that's an outlier. 2200 is an outlier. 4900 is not an outlier. And then on the upper end, it looks like 7200 is an outlier, 6800 is an outlier, but 6000 is not. So that's how you could identify the outliers in the data set, like identify what the actual values of the outliers are. So our outliers are 530, 2200, 6800, and 7200. But now to verify that, we would want to compute the fences, right? So if you have room, you can kind of squeeze in those calculations. And let's see what we get, right? Lower fence. Okay, so for the lower fence, you should get 4425. And then for the upper fence, you should get 6625. Okay. So you can see why 530 and 2200 were outliers because they're both below that lower fence. But 4900 was not an outlier because it's not below the lower fence, right? Whereas, and then on the upper fence, we can see that 7200 and 6800 were outliers because they're both above 6625, but 5800 is not an outlier, 6000. Oh, it's easier to look at this in Art of Stat, isn't it? Because here the values are already in order. So yeah, so 6800 is an outlier, 7200 is an outlier, but 6000 is not. And again, when you hover your cursor over, it's calling 4900 the lower fence, but that's not correct, right? The lower fence is actually 4425, and it's calling 6000 the upper fence, but again, not correct. The upper fence is 6625. So anyway, hopefully that makes sense. It's unfortunate that Art of Stat mislabels things that way. Then again, maybe it's not a mislabel. Maybe it's just a difference in terminology, right? Different people use the same words to describe different things sometimes. But in this class, the fences refer specifically to these numbers. They don't correspond to anything that's actually in the graph, right? 6625 would be, somewhere here, and 4425 would be somewhere here, right? But we don't actually indicate those on the graph. Okay. Last topic here, I want to spend a little bit of time comparing box plots and histograms because they're both used to visualize numerical data. And so you may wonder, well, why do we need two different graphs? The answer is they have different strengths and weaknesses. They display different things. And so we usually like to look at both whenever we're trying to describe a numerical data set. Here are some connections that hopefully you can make in your mind. So note that while the bars in a histogram are usually all the same width, the regions of a box plot are usually not all the same width, right? We've seen that previously, right? The regions in the box plot, this whisker is much longer than this little region and so forth, right? So the regions of the box plot are not all the same width. So that's one difference between them. Histograms, the reason that histograms all have the same width is because histograms bin the data into classes of equal width, regardless of how much data falls into any given bin. When you make a histogram, sometimes there are bins that don't have any values in them, right? But they always make the bins the same width, regardless of how much data falls into any given bin. Box plots do the opposite. They bin the data into classes of different widths, so that each bin contains 25% of the data. That may take a little while. You might have to rewind and play that again and really pause and think about that so that until it makes sense in your head. But the moral of the story is this. I think that box plots, generally speaking, are better at identifying outliers, whereas histograms are better at showing the shape of the data. With that said, you can tell what the shape of a distribution is by looking at a box plot, roughly. Histogram's a little bit easier, but box plots, it's still possible to do this with box plots. And in the same way, I would say you could look at a histogram and kind of tell when you've got an outlier, but a box plot's going to be much better at identifying outliers. So again, we'd like to look at both. But roughly speaking, here's how shapes correspond to one another. If you have a skewed right distribution like this one, then the box plot's going to look skewed right. The box plot's going to look like you started with a symmetric box plot, but then you yanked on the right-hand side to make it longer, so it looks skewed right. With a symmetric data set like this one, the box plot's going to look pretty darn symmetric. The median's going to be right in the center of the box. The whiskers are going to be the same length, roughly. And then if you have a skewed left distribution like this one, it's going to look like you started with a symmetric box plot, but then pulled on the left-hand side, right? So it's skewed, pulled on the left-hand side so that it's skewed to the left. Okay. So we'll do one more example. It says, open up the data for 1.4 spreadsheet and navigate to the example 6 tab. Use Art of Stat to create side-by-side box plots and stacked histograms of the data. So we'll do that together. And then we'll have a bunch of follow-up questions. So let's head over to Art of Stat. First of all, pulling up that data set. This is example 6. We've actually got 4 data sets here. So we want to compare 4 data sets. So maybe let's look at Art of Stat because this is what we would use if we wanted to look at just a single variable. But if we have several groups that we want to compare, then we need to click on this tab up here. And we'll need to do our own data set. We'll have, in our example, it looks like we have 4 data sets that we want to compare. So I'm going to change the number of groups to 4. See, now you have space to put in the data for each of your 4 groups. So I'm just going to copy and paste each of these. Control Shift down, Control C to copy, Control V to paste. And we'll do that 3 more times. As kind of tedious and monotonous as this is, imagine if you had to enter the values by hand. That would take us forever. One more. Okay, and as soon as we get the data for that 4th data set in there, it calculates the descriptive statistics for each of those 4 data sets. So in particular, Q1, Q2, Q3, and IQR. And then it also makes these side-by-side box plots, which is really nice. We were also asked to make stacked histograms. This is something that we haven't really talked about, but if you just click on this histogram button, then it'll give you stacked histograms. What's really nice about this graph is that it plots all 4 of these histograms on the same x-axis, so that you can see, like, oh, the average, value in group 4 is obviously smaller than the average value in group 1, right? And you can look at the shapes of the distributions here, right? This is symmetric, this is skewed left, skewed right. This one seems fairly symmetric as well. Anyway, when you're using this particular tool, you don't have a lot of freedom in terms of your bins. So I wouldn't advise using this to make just a single histogram. But if you're trying to compare a bunch of groups, looking at this stacked histogram thing is pretty nice. And by the way, I don't think I've shown you this, but you can download these, or you can, you can download. If you click on this little button, you can download these. If you want to include this in a problem set or a test or something, instead of having to draw stuff by hand, you can just download the image and then, paste the image into your document. Anyway, back to the box plots. Let's see what we're asked to do here. Part A says identify any outliers in any of the data sets. Well, I'll let you pause the video and do that. Here's my solution. Group 1 clearly doesn't have any outliers. Group 2 doesn't have any outliers. Group 3 has a whole bunch of outliers down here. And then group 4 doesn't have any outliers. So for group 3, we can't put the values in order. Hopefully they already are. Yeah, they are. Smallest to largest. Looks like. Oh, goodness. There's a lot of data for group 3, huh? So on the lower end, it looks like the smallest value that's not an outlier is 31. So all of these values below 31, those are all outliers. 18, 22, 22, and 23. But then there are no outliers above it, right? So those are our 4 outliers for dataset 3, and the other 3 datasets don't have any outliers. So I'll say only. Hold on. So I'll say only group 3 has outliers. They are 18, 22, 22, and 23. Okay, part B, identify the shape of each distribution and verify that the box plots and histograms match each other in this regard, in the sense that they have the same shape. Let's look at the stacked histograms for this, and we'll come back to the box plots in a second. But yeah, I would say groups 1 and 4 are bell-shaped, symmetric, roughly. Group 2 is skewed right, and group 3 is skewed left, right? That's how I would assess this. To see if that matches with the box plots, yeah, group 1 looks pretty darn symmetric. Okay, group 4 doesn't look quite as symmetric as group 1, although you'll notice, like, here this side of the box is bigger than this side, but this whisker is bigger than that one. So you know, they kind of balance each other out and make for a symmetric distribution. Group 3 is clearly skewed left with a bunch of outliers out here, and group 2 is clearly skewed right. So yeah, I would say the box plots and the histograms match each other pretty well. Group 1, bell-shaped. Group 2, skewed right. Group 3, whoops. Skewed left. And group 4, bell-shaped. Okay, which group is most spread out? Well, that depends on how you measure the spread. So this is something that we'll talk about in a future section, right? How we measure spread. But I think in this case, there's a pretty clear winner, because if you look at group 1, it spans all the way from the smallest minimum to the largest maximum. And even if you ignore the whiskers, the box itself is more spread out than the other 3 boxes. So I would say group 1 is the clear winner in this case. Group 1. And then part D, which group has the largest values on average? Which has the smallest values on average? Well, again, that depends on how you measure the average. And this is something that we'll talk about in a future section as well. Okay? But in this case, if we just take kind of where the center of mass is, so to speak, like if we take the center of our boxes, in other words, the median of each box, we can kind of compare those pretty easily. Looks like group 3 has the largest average value. And, it's a close call between groups 2 and 4, but I think group 4 has a slightly smaller average than group 2, right? A smaller median. So I think group 3 is the largest, group 4 is the smallest. Okay. And that will do it for this section. Thanks for hanging in there, and I will check in with you on the next one.